The fourth physical property that we're going to discuss about organic compounds is related to the electrical conductivity of different homologous CDs. Now, the first thing is, as we've already discussed, that almost all organic compounds, they are covalent compounds. And one of the property of covalent compounds is that they do not conduct electricity. So they're not going to conduct, they do not conduct electricity in molten liquid or gaseous states. So they're not going to conduct electricity in molten liquid or gaseous state. But there are a few exceptions. Those exceptions include compounds like carboxylic acids. So one of the exceptions that is going to be conducting electricity is are carboxylic acids. And the reason why carboxylic acids conduct electricity is that they ionize, or they partially or weakly ionize, weakly or partially ionize in aqueous state. In aqueous state, which means that they form ions, and when you have ions in aqueous state, they are going to conduct electricity. So we can take the example of ethanoic acid, and I'll show you how ethanoic acid weakly ionizes. So let me underline carboxylic acids because it's an exception. So let's draw ethanoic acid, which is this is the carboxylic acid functional group, and when you mix it in water, when it is in aqueous state, let's write the word aqueous underneath that. So when it is in aqueous state, it weakly ionizes, it breaks up into ions, and one of the ions that is formed is this ion, and the other ion that it is going to produce is the H+1 ion. Because it's an acid, acids, one of the properties of acids is that they produce or they donate H+1 ions. They are proton donors. So this is what's going to happen when you mix ethanoic acid or any carboxylic acid, or any carboxylic acid in water. They're going to partially ionize. Now the stress is on the term weakly or partially ionize, which means that they're not going to produce a lot of ions. So they will conduct electricity, but they won't be very good conductors of electricity due to partial ionization. They won't be producing a lot of ions. So compared to strong acids, carboxylic acids, on the other hand, because they're going to be weakly ionizing, they will not be producing a lot of ions. Carboxylic acids are therefore poor conductors of electricity. And it doesn't mean that they're not going to conduct electricity. They're going to conduct electricity, but when you compare them with strong acids like H2SO4 or H3PO4, which strongly ionizes, which produce a lot of ions, these carboxylic acids will not be very good conductors because they have fewer ions. And remember, electricity is the movement of charges. So if ions are moving around, that is a form of electricity. Then there are other organic compounds which are also going to be conducting electricity. One of them one of the other organic compound that's also going to ionize when you add it in water, and that is those are amines. The reason why amines are going to conduct electricity is because they're very weakly basic. So these are weak bases, and I'm going to give you the example of let's say ethylamine. I have ethylamine, which is CH3, and it has N bonded to 2 hydrogen atoms. So if you add it in water, what's going to happen is that it's going to accept, and let me correct this, it's this would be a reversible sign. It's a weak base, which means that this reaction is reversible. It's going to reverse, it's not going to ionize completely. So if you have ethylamine, then it would be accepting H+1 ions from water, and when it does that, this nitrogen gets a positive charge. So ethylamine gets positively charged. On the other hand, it ends up producing OH minus ions. So ions are produced when ethylamine is added to water, and whenever you have ions, electricity would be conducted, but they won't be very good conductors compared to strong bases or alkali. So it's a weak base or alkali. The reason is that it's also going to partially ionize, partially or weakly ionize. So they're going to be poor conductors of electricity as well. Conductors of electricity, as fewer ions would be produced and you're comparing them, and this is true only when you're comparing them with strong bases or alkalis. So only when compared to strong bases or alkalis. So remember this, that amines and carboxylic acids, only they are going to conduct electricity when they are in aqueous state. Other organic compounds like alkanes, alkenes, etc., they will not be conducting electricity. They're covalent molecules, they don't dissolve in water much, and they don't ionize in water, so they're not going to be conducting electricity. They're not going to be forming ions. They don't have any charged particles. They don't have free moving electrons or positive ions. So this is an important point. Remember, if you get a question which states whether something is going to conduct electricity or why something is not going to conduct electricity, the answer must be that if somebody asks you whether carboxylic acid or amines are going to conduct electricity, they're going to conduct electricity due to free moving ions, not due to free moving electrons. They don't have free moving electrons. Only metals have free moving electrons. The fifth property that applies to almost all organic compounds is that they combust. They are all flammable, and they all react with oxygen. To produce carbon dioxide and water. Mostly it's going to be carbon dioxide and water, because I'm talking about hydrocarbons right now, which contain carbon and hydrogen mostly. So most of the time they're going to be producing carbon dioxide and water, and all of the reactions, combustion reactions, are going to be exothermic. They are one of the major sources of energy in the world fossil fuels are all organic compounds, and they are a very good source of energy because they are exothermic and they are easily available as well. So they react with O2 to produce CO2 and H2O. There's another thing: if the reaction involves, if it is done in a limited supply of oxygen, if the same combustion reaction is performed in a limited supply of oxygen, then your products would include carbon. Products would also include carbon and carbon monoxide. This is when you have incomplete combustion. So limited supply of oxygen means that the reaction is not going to completion. There is incomplete combustion. There is incomplete combustion that is taking place. Now I'm going to do a few examples of some combustion reactions of organic compounds, and let's start off with alkanes. Let's say I have butane, and I'm writing down the reaction for the complete combustion of butane. Now butane, if you remember, the general formula of alkanes is CnH2n plus 2. So if I apply that, but would contain 4 carbon atoms, and it would contain 10 hydrogen atoms. Now if I react it with oxygen plus O2, it's going to produce it's going to give me CO2 and H2O. Now I need to balance this equation. Now this equation will be balanced since there are 4 carbon atoms. There should be 4 carbon atoms on this side as well. Similarly, there are 10 hydrogen atoms on the left hand side, so there should be 10 hydrogen atoms on the right hand side as well. So there should be 5 water molecules. And if I count the total number of oxygens on the right hand side, that's going to be 4 into 2, that's 8, plus 5. So I have 13 oxygens on my right hand side. So there should be 13 oxygens on the left hand side as well. So the number of oxygens on the left hand side, it's going to be 13 over 2 because you have O2. And to make 13, since one oxygen contains 2 oxygen atoms, 6.5 O2 are going to contain 13 oxygen atoms. So now this equation is balanced, and I can rub this off. Now this is one equation, and similarly we can construct an equation for combustion for any compound. Let's take, for example, let's do the same for ethanol. Now ethanol, the general formula for alcohols is CnH2n plus 1 OH. In ethanol, N would be equal to 2, so H would be equal to 5, and I am reacting it again with O2, and my products are going to contain CO2 and H2O. So these are my products, and I just need to balance this equation. So if I balance this equation, the 2 carbon atoms on the left hand side, there should be 2 carbon atoms on the right hand side. There are 5 plus 1, 6 hydrogen atoms over here, so there should be 3 hydrogen atoms, 3 H2O molecules. That is going to make 6 hydrogens on the right hand side. Now I have 4 oxygen atoms over here, and I have 3 oxygens. So that's a total of 7 oxygens on the right hand side. Now there's 1 already over here, so I just need 6 more oxygens. So this would be 3 O2, and I can now erase my working. Similarly, we can do one more example. Let's take the example of let's think of a bigger molecule. Let's think of a molecule like decene. Let's think of decene is going to contain 10 carbon atoms, and it's an alkene. So the general formula of alkenes is CnH2n, which means that hydrogens are going to be double the number of carbon atoms, and it's going to react with oxygen in exactly the same way. So you have CO2 and H2O as the products, and I'm going to try and balance this equation. Now there are 10 carbon atoms on the right hand side, because there were 10 carbon atoms on the left hand side. There are 20 hydrogens on the atoms on the left hand side, so there should be 10 H2O molecule. Now that's going to be 10 O2, means that there are 20 oxygen atoms in this molecule, and there are 10 over here. So that's a total of 30 oxygen atoms on the right hand side. So this is going to be equal to 15 oxygen molecules. So that is how we're going to balance the equation for decene. Now we're going to try and do these equations later on as well. Just remember, whenever you're talking about a combustion reaction for any homologous series, you react it with oxygen and you produce carbon dioxide and water, and you're going to balance that equation later on. The last point, and it's a very important point, the last important point is, and this applies to all organic compounds, and that point is that as the size of a molecule increases, as size of molecule increases, its flammability, on the other hand, it's going to decrease. So its flammability would decrease. One of the reasons is that smaller molecules have more. They have lower boiling points, which means they're probably going to be existing in the form of gases, and gases are going to react more readily. They have more kinetic energy. They have more surface area. They can mix more readily. So smaller molecules. One of the reasons for this is that smaller molecules have lower boiling points and melting points, boiling slash melting points, so the entropy is more, and since they have more entropy, entropy is a term that is used to describe the state in which a particle is. If there's more disorder, there's probably going to be more collisions. So more entropy would result in more collisions, and inadvertently or indirectly, it's going to result in more. It's going to result in a faster reaction. So remember this fact, that as the size of molecule, this is a very important fact, as the size of a molecule increases, its flammability would decrease. So generally we want smaller molecules. Smaller molecules are more useful. They burn more easily. They have low melting and boiling points. They're going to exist in the form of gases or low boiling point liquids. So smaller molecules are more useful. I can give you a few everyday examples. For example, in most domestic heating, they use methane gas. Methane gas only has one carbon atom. It's a small molecule. It's a small molecule. It burns very easily. On the other hand, you can have another example like candle wax. Now, candle wax has it's a very large molecule. It contains molecules which are very large, so large. It's made up of very large molecules, and it, on the other hand, it burns very slowly. So those are some of the examples that you can bring up when asked about the flammability of different organic compounds, and this applies to all the homologous series. So whenever you're talking about homologous series, the smaller molecules are going to be more flammable, and the larger molecules are going to be less flammable.